So, hello everyone. Today, let's have some discussion and explanation that has to do with SLD, which has to do with the singular diagrams of electrical distribution network. And I'll be talking about this substation, as you can see on the screen. So, this is substation 3405. And if you can look at it very well, you will see it's a distribution network that is having two in common. And let me quickly label it. Let's say we have in comma A and we have in comma B from this substation. And they are both fed from two transformer, which is 11 kV, 11 kV to um, for 33 kV. It's a step down transformer away. So, and then it contains of 415 main LV switchboard, as we can see from QD25 from here. So I hope not to spend more than 10 minutes so that I'll be able to upload it on the system. And uh, let's dive into it. Firstly, this when you think about this drawing, it is like a map of electricity. You know, electricity comes from power station and it enter into substation, and from there it is being shared to different places in the building, the lighting, machines, and the rest like that. It's like let's say we have a power station. Let me quickly bring this down. The power station, right? From there, it goes to transformer, and from transformer, let me bring main board, main switch board, right? And then from there, breaker. Let me put breaker, right? And to buildings, uh, buildings, machines, right? And just like that, and just like the etc. Now, as I've said earlier, we have two in comma. Um, because of redundancy. So if you have two income from the same source, you have redundance. But two income from different source, you have more redundance. I hope you can get that point very well. So the substation name is 3405. As you can see, we have the panel source here. The panel source here, if we can zoom it very well, we see the panel name is here. The panel name, right? Um, panel name is here. Panel name of the source of the incoming power, and then the source substation is this one. The source substation. Let me put it here. Source substation is this one, right? So it comes down to the cable. I don't want to forget this. This is the cable size. We have the cable name here. We have the cable size. And then quick one here, we have uh, 3 core 150 square cable. Okay, let's say you have that will be RYB, right? Cable. Okay. Now you have the PVC here. You have the hammer. Let me bring it here so that I'll be able to bring the cable configuration out. And you have the XLP here at the back as a jacket, the cable. So it means you have um, the copper, you have the copper, which is CU, right? And after that, you have the PVC will be here. We have still our wire hammered here, and then we have XLP here. Brilliant. Now, so in order for me to be able to write the full configuration of the cable, that will be CU just to do with the copper, with PVC, with steel wire anode, the XLPE, right? So since my cable is, what the size of my cable here? This is 150. So with my cable of 150, I can go with a one core um, plus 75 according to IEC. 75 meter square cable is enough for my grounding earth continuing conductor ECC. Okay, because as per I see, when you have from 0 to 16 square cable, when you're looking at the grounding, you use the same cable, right? The same cable for grounding, right? But from 16 to square, from 16 to 35, right? We use 16, right? For the grounding. And above 35, that is above 35 square cable, it means you are going to consider half of the size of the cable, right? Half size of the cable. So with this fundamental information, it means I have 150 from the cable size here. I'm having 150 square cable. It means 150 divided by 2, then I'll be having like 75 square cable for the for my grounding, right? So I'll be considering that if it is required. Let me just clean to have more space for more explanation. Now I'm still on the cable explanation for coming from the incomer, right? So now I'll move straight down to the transformer. I have transformer here. Let me just bring the transformer here. Let's see what we can discuss regarding transformer here. Now, I have a transformer here, which is from primary 11 kV, primary. That's my primary voltage, right? That is 11,000 volts, right? So, and my secondary, I have 415 volts here. Uh, my um, secondary will be 415 volt, yeah. That's why this SLD. Okay, now, though it is 433 kV, well, let's consider it as 415 volts so that we can move forward. Now, because most buildings and machines cannot use a very high voltage safely, okay, so transformer act like a power reducer. It brings down the voltage level, right? Now, the size from here, so the size of this power transformer with 1250 kVA, transformer is in kVA, and that's the transformer capacity, transformer uh, capacity. Okay. Now, what about the current current capacity? I think when you use when you use the formula of square root 3 of voltage cos theta, you're getting the transformer and make the current the subject of the formula. It means you'll be getting the capacity of the current capacity of the transformer, right? So from here, we have the power of the transformer, which is 1250 kVA. We have the cooling system, right? ONAN, it has to do with the cooling type, which is oil natural, right? Oil natural, hair natural, right? Hair natural, right? Of the transformer. And then we have here we have the then DYN11, which indicates that we have the vector groups, which has to do with the primary is delta. The primary is delta connection. Primary is delta. Let me put it here. And then the secondary is star plus neutral. Secondary is star plus neutral, right? Okay. Now, still under transformer here. So we have impedance, which is 5%. Impedance, which is 5%. It means transformer impedance, which is very, very important for short circuit calculations. Okay. Now, a quick one because of the time. When you look at this type of electrical map, it looks like a water pipe, right? That you have to split the water into different houses or into different apartments within houses, right? So now we have a breaker here, which is a circuit breaker, which is a AB ACB, why, which is 2000 amps, right? Let me see if I can use this so that we can see it very well. 2000 watt, 2000 amps, which is automatic switch, right? So when there's short circuit, when there's a fault, overcurrent, or any problem in the system, it automatically switch off. So we have incoming breaker of ACB, which is 2000 amps, which is a normal close. Okay, so this breaker feed the bus bar and bus coupler within the two sections, right? This is normal close, this is normal close, and this is normal open. Okay, so this breaker, especially this one in the bus coupler, right? Here in this domain. So this breaker connects both the bus sections. If the transformer fail, the system here is they normally call it uh, sectionalizing, right? The one of the main function here is for load sharing, right? If you want to share the load, uh, or redundancy, also very important. The uses for redundancy, right? And what's come to my mind now is for maintenance also, right? For maintenance, flexibility, yeah. Maintenance flexibility is also very useful for that. So I think it is good to stop here and then I will continue in the next section. Thank you for listening.